we will split the talk up into 3 pieces. I'll start out and then hand it off to Brady, who will hand it off to Patricia, and then we're going to let Mung talk about costs, or maybe I should, to make it a little softer. Okay, we'll see what happens at the end. Okay, so this just gives you an idea of what we're like. Can they hear me if I'm back here a little bit? Okay. So, you know, we've introduced ourselves, the PI, Stokey, the co-PI, Cox, the co-PI, Clayton, and we're quite wise, so we have the dean, who has money, who is senior personnel. It's even better than that. You can't pay for them because their salary's totally covered, so she's a freebie. The operations manager is paying you. The hydraulics technician that is the full-time person with us, really, is Andrew Valentine, and he's a wonderful person to work with. In our cybersecurity, as they all are, by the way, in our cybersecurity and the jack of all trades, really builds equipment and so forth, is Robert Kent. And the retired person who comes back and helps us and gives us direction, and I think was born only a few years before ViperSize started. It's not really true, but he was with the firm that started Conoco, and I think has been listening to ViperSizes for 50 years, maybe, certainly 45, and he'll just walk up to ours and say if they're working properly or not. It's quite remarkable. So we'd be in trouble without him.
I got you.
Did you do that? Okay, good, good. Okay, so we are not here. This is the University of Texas facility. Here's the main campus, and that's where we're located with our equipment. Okay, so here we go. This is building 46 out there at the Pickle Research Campus. It's not Heinz Pickles. It's Jake Pickle, who was our congressman. We're here in building 46. We only got half. The structures would only give up half, so we have half of this building. That's where our equipment is located. If some of it isn't in here, this has been paved and so forth. But we have nice space out there to have field equipment and be able to work with it. And so this is looking into the building. So here, structures was on the other side. We're looking into the building here. You can see that's going to be Thumper, the small one. I don't know which one it is. It's either T-Rex or Liquidator, and we can't see that, but that's the RDD, I think, in there. And this is just with those machines out, and we were building sensors when we went to New Zealand and did testing down there. And it's really great to have that kind of space. Now, the problem with this space, if you will, is that it's not air conditioned, and we live in Texas. So we have the air conditioned space, that's okay. We have the air conditioned space for the technicians and so forth, and offices, if so to speak. It's very nice for us, in fact. Okay, so this gives you an idea of what we're looking at here, and we're trying to offer you in terms of capabilities of shaking and mobile shakers, and up to now it has always been just one, but we're working on phasing 2 together. But here's Tri-Axial T-Rex, a Tri-Axial shaker, so that's what's here. It can go vertically, horizontally, longitudinally along the length of the machine, and horizontally perpendicular to the machine, one at a time. You're flipping between them. It weighs really about 68,000 pounds because of other things we put on the back, but is pretty much one of a kind. We think the others that have been sold to Russia aren't working, so we'll see. Doesn't matter. For you and for anyone else, it's one of a kind. Liquidator is truly one of a kind. When we started as NEAS, Network for Earthquake Issue Simulation, which lasted for 14 years, 4 years of building, 10 years of operation before this, that was specially designed for us to be a low frequency shaker, because you get in the earthquake business, you start to try to profile deeply or start to try to load things maybe really at low frequencies. This is special, and what's special about it is it has to have a lot of travel to create good loads at low frequencies, and you'll see how we got even bigger loads here in a little bit. But yeah, Liquidator, we've only used it in the vertical mode, and we're told it takes about a day and a 25-ton crane or something like that to rotate it to the horizontal mode. But we haven't been too excited about doing that because it's doing such a good job for us just in the vertical mode. It's sort of touch and go to do that. Okay, then to go in the cities, you need a small shaker that doesn't attract lawyers. So Thumper is one of those, and it can be X, Y, and Z. Also, it just takes a couple hours. I think, isn't that about what you have it down to, something like that, to change the shaking mechanism in the back so it can go in the different directions. We were working a lot with Lawrence Berkeley National Laboratories, and they had a bunch of shakers on the top of Yucca Mountain. And when we were doing work, and when I first started working out there, I rented them from them. But they then offered us some that were going to just be cut up for scrap, just going to be tossed out when the Yucca Mountain project was ending. And they even shipped them to us. So here are two that we use. This is a mid-sized vertical shaker. It's not quite as large as T-Rex. And this is the horizontal shaker, which is as large or a little larger than, if you talk about horizontal shaking, than Liquidator would be. We've got a big rig to move it around. Why? Because when you start going out and doing research, and if you go from location to location with these big shakers, you really can't afford to have people, okay, bring the truck back, move it for us. Okay, go away now, bring the truck back, move it. So our operators also can drive this. I think it's one of the things maybe Professor Cox has wanted to drive for a long time, but hasn't, as far as I know.
The big rig?
Uh-huh.
Yeah.
You haven't, have you?
That's maybe the one thing.
Okay.
He wouldn't tell you if he did.
That's what, no, he would. He would enjoy telling me, I think. Okay. Haha, he did. Okay. And then we have different vehicles. We've got a field support truck, but it's got a 100-gallon tank here for the diesel fuel so that we don't have to call people to bring that in, and that's to save money. It hauls this trailer, the new trailer version of that. So we have a trailer. You'll see it in the next slide. And we've got a cargo van, and we've added, when I said we added things on the back, that little top right there, and that little thing sticking up right there, it sticks up off of this, but it's a hydraulic cylinder, so we can push sensors in the ground, and we can pull them out, and we can run cone penetration tests with Fugro penetrometers and things like that we own. So that's very helpful to us. Thank you. Okay, so we'll go through each one of these just to get a sense of where we are. And what you'll see on these drawings is the peak force and the frequency log scale. But all the different shakers we just heard about are on here, and it shows you the relative comparison. So here's T-Rex in the vertical mode, and we're going up to 60,000 pounds basically. In fact, I think we keep it closer to 55, but right around there. And then here's the frequency range. So you see the peaks there at 12 hertz. We don't like to go and show above 100. We don't like that. It's hard on the machine, but it gives you a sense there for that large output. Then horizontally, it's half as much, basically just thinking the coefficient of friction is a half for sliding. And if you try to go to a higher horizontal force, you don't have enough hold down force, and it starts to slide on you. So here's T-Rex in the horizontal direction, as they say. And, okay, wait till we get the liquidator. So, this is going to be Professor Cox speaking.
Yeah, this is a short video from testing in Christchurch, New Zealand. I don't think our speakers are working, but okay. I can annotate.
Remember what you said.
We'll talk a little bit more. We shipped T-Rex down to New Zealand. It's been maybe a couple years ago now to do some testing, deep surface wave profiling, and you can see the vibrations from the truck kind of being carried out into the water at this location. But
water on the bridge.
Yeah, you'll get to experience this live tomorrow, so we don't need to dwell on that too long.
Okay, then here's liquidator. It's on the top of the other mountain right there. And you see how much lower the force is in the vertical motion. But here is where we have the extension, and that's really important when you start profiling into the ground with surface waves actively. So that's the main reason for this. It's the same in vertical and horizontal because it's got a very large hold down force. So it's really the stroke. In fact, we're going to see it move.
Yeah.
So here's that orange mode I should have told you. So there's nothing else that does that. I mean, that's a huge shaking motion, but at low frequencies, you've got to have that to get the forces out. Okay. And the thing I should have told you is everything that's white holds down the orange. And also everything that's white is a hold down force. And in fact, the hold down force comes through just two hydraulic rams to hold down the base plate of the machine. Next. So I was after FANU. I think this is a pretty correct statement. We got to get more force. We got to get more force. How are we going to do? We want to do. He said, no, he didn't say it this way, but no, those aren't very good ideas. And so I think in the middle of the night, one night, I popped up and said, okay, we're going to lift the whole darn machine up and down. And I can say those things, but I can't do it. FANU did. And so now that's 55,000 pounds that you're shaking with. And we went down to, is it 0.6 or 0.65 hertz?
Yeah, 0.65.
0.65 hertz. And we were, all of us were working on a greenfield project in Columbus, Georgia. And we had to build a slab for us on the ground to give us a little more stability than just basically on soil. But we put out our sensors, boy, we were really going to do great work, and we did great work. It's just we generated a 2-mile-long wave, and I never thought we could do that, but we were at a pretty stiff site, so we didn't see that part out. But we did active and passive, oh, it's not passive, a passive guide and an active guide, and we did those together, and it was spectacular. So we went down to at least 2,500 feet with strong resolution and got into about, let's say on an average, 9,500 feet per second bedrock on the East Coast with good engineering measurements. That may be the first time that's ever been done. And so we're very pleased. And so we hope we can get into the National Science Foundation's pocketbook as well, but we'll see what happens. Okay, so here's Raptor. Raptor is a little smaller. It's a vertical one, but it can be phased with T-Rex. Next one is Rattler. It's a little smaller, but so it's shaking this way. It can be phased, and we have a project, by the way, in liquefaction. And FANU has already had Raptor and T-Rex out phased together. Now we can phase them, not in sync, but at angles. But that we doubled our amplitude, and that's huge. When you get to near liquefaction, we haven't gotten near liquefaction, but that should have a really big impact on our project that we have. So we'll be doing that testing next spring to summertime. And you know, whenever I talk about some of these things, for everybody, NSF loves piggyback projects. So if you know about something we're doing, they would love to have you submit some smaller project to piggyback on top of this, and you would just make us look good, by the way. So we would appreciate that if you would come up with ideas like that. So it would be very helpful to you. Did I mention that right? As I did.
Not yet.
It's just a smaller one. So you see how small it's just a smaller one, but it's very good and it's very useful in many different applications. Okay. There's a big rig in action. Now, so that's our field truck, but with the fuel ability to supply fuel, that would be a typical trailer. We have a little bit, is it the same size as you?
Yes.
Okay, same size trailer, but a more robust undercarriage, so we don't blow so many tires going down the road because it's full of stuff. The back is dirty, the front is air conditioned, and so the instrumentation is in there. In fact, you're going to see a guy sitting there, and maybe in a minute, and see if you can identify that person. Oh, you were too fast.
Good
No, I
introduction.
wanted to do the other one. Yeah, there's a cargo van in the smaller trailer. Yeah. Okay. Okay. Your hair looks a lot redder today.
I had more hair, and it was a darker.
Is that what red hair like this brain does?
I guess so, yeah.
Okay, I don't know. You're up.
Okay, I'm going to quickly talk a little bit about our instrumentation that we have. Our data acquisition systems, we have several. We have a 72-channel VXI system, 24-bit dynamic signal analyzers, up to 50 kilohertz simultaneous sampling rates, so they're not multiplexed. This one's a little bit older. We don't use it as much. We brought it here with us in case we needed it, but mostly we're using this system, the 64-channel data physics, again, dynamic signal analyzer, 24 bits, and up to 200 kilohertz simultaneous sampling rates, no multiplexing. And both of these analyzers have real-time frequency domain capabilities, which is really nice, and they have anti-aliasing filters and all kinds of stuff. So it's good when you're sitting there in the field to be able to look at the time domain and the frequency domain. You can write functions to easily do different transfer functions and stuff like that. So they're really good analyzers, very high quality, and if you can give us an analog signal, we can record it with these, essentially. In terms of instrumentation, coming from the geotech world, a lot of our instrumentation are velocity transducers in one form or another. So we have 109 1 hertz geophones, 85 vertical and 24 horizontal. We have over 15,000 feet of cable to string these things around. This happens to be using these 1 hertz geophones, again in New Zealand, for MASW multi-channel analysis and surface wave testing. We also have 10 of these nanometrics broadband seismometers. We record active vibrations with these, but mostly they're used for recording ambient vibrations. Each one of these boxes costs almost $20,000 about. They're extremely sensitive. They have a flat response from 120-second period, clear up to 100 hertz. And again, there are 3 components, very good at digitizers. We use these on a lot of different projects. We've used them here. We'll show some data from some of those later. In terms of subsurface instrumentation, we have standard cone penetrometer probes that we can push into the ground to do seismic CPT or regular CPT. We have our own sensors that we fabricate a lot that will hook to rods, and again, push them into the ground, oftentimes decouple them from the rods, pull the rods out of the ground, leave the sensors in the ground. Also, one thing that we want to make clear for those of you thinking about using our site, if we don't have the sensors you need, there's additional instrumentation resources from IRIS Pascal, which is an NSF-funded center that's housed in New Mexico. And for example, here's just some of their kinematric epicensors, which are a very common tri-axial accelerometer that's used for a lot of structural testing, at least in the earthquake engineering field. Have mobile shakers, will travel. That's kind of our motto. Before NHERI started, this is in the NEAS days, as Professor Stokey mentioned, we operated for 10 years under NEAS, and these are kind of locations or dots of places that we did various types of testing, including Hawaii. I was there. It was great. That was 2 weeks of surface wave testing with our thumper truck, the smaller truck on the Big Island.
He got one in his picture to be taken amongst all the pretty flowers. They made them look good.
Flowers? Is that what it was? Okay, all right. New Zealand. Again, New Zealand. That was T-Rex, and we'll talk about New Zealand later. But in terms of just a quick snapshot, these are various pictures of T-Rex being used. This is the Hanford site in Washington, where this was for a vitrification plant to look at solidifying nuclear waste. And landfill in Los Angeles. We've been at Los Alamos National Lab testing these things are called hoodoos, which are these little precariously perched rocks. And people try and back out earthquake ground motions from historic earthquakes, and they say, well, if this rock is still standing here, the single degree of freedom oscillator on this pedestal, the ground motions couldn't have been larger than whatever. So we would test those dynamically. That was kind of a fun project. Thumper, this is on the big island of Hawaii at 13,700 feet on the top of Mauna Kea volcano. So you go from sea level up to 13,700 in a day, a couple hours. That was, some people get a little lightheaded.
What almost was a troublesome thing that happened up there?
I'm not sure.
Remember, it couldn't start the engine to lift it back up.
The truck was a little, it didn't like being at altitude. Yeah. And we've been in the mountains of Utah doing topographic amplification studies, and on the campus of Stanford, and all over the place with Thumper. And the liquidator, again, is used often for surface wave testing. Professor Stokey mentioned the Yucca Mountain, so we've been at the Yucca Mountain site a lot, in Imperial Valley, California, and the Mississippi Embayment, the Salt Lake Valley. The list goes on and on. A lot of nuclear power plant work. So these are some of the types of projects that we had used the trucks for in the past. However, we have a...
Can I say one thing?
Yes.
Just, you should realize that we're not fully funded. So the National Science Foundation doesn't give us 100% funding for all the people you saw there at all. So we have to take some other jobs through the university court, and we can't earn consulting, but we have to take other jobs that help pay for our technicians and also give us, what do we call it, profit paying?
Program income.
Oh, program income.
Program income.
We use the word profit. Well, at a public university too. So we can't use the word profit, but that keeps us going. So when you see some things like that, don't get the idea we're out there consulting, because that isn't true at all. And sometimes it just can be misleading. Okay.
So when we applied for NHERI, when the NEAS program was kind of dissolved, we had to come up with a science plan and to discuss what was our vision for using this equipment in the future, and why should NSF, for example, fund our site. And these are three things that we planned in our science plan years ago. And lo and behold, if you plan it, it will come to pass with some hard work and help from good friends who help you with achieving this. So we planned our science plan around subsurface imaging, in situ nonlinear testing of soils, and structural health monitoring and soil foundation structure interaction. And we've had now 3 workshops, including the one today, where we've invited people to come to do testing on a levee in St. Louis, Missouri, in situ liquefaction testing in Portland, Oregon on silty soils, and now testing of a bridge. And we'll talk about each one of those kind of science plan visions. We want to publicize ourselves, obviously, because we want people to use the equipment, and it's cheap. Right, Renata?
Yes.
It's cheap if it's an NSF funded project. It's pretty cheap. We'll talk about costs later. In terms of our science plan number 1, our vision was to perform deeper, more accurate, higher resolution 2D and 3D subsurface imaging, geotechnical imaging. Thinking about the ultrasounds of the past and the advancements that have been made in medical imaging, you can now go to the mall. I have 4 daughters. I've been through this 4 times.
Is that one of them that you used up
This
there?
is not
Oh,
one of
okay.
my children.
You had never
That's
mentioned
right.
before.
I
I
don't
didn't
know
know.
whose child this is.
Okay.
I apologize if you're out there and you didn't intend that use, but 3dbaby.com. You can check it out. So we need to do the same thing with geotechnical imaging. Currently, we're pretty much living the 1D world. We go out, we drill a borehole, or we push a cone, or we get a shear wave velocity profile, and it's one-dimensional almost always. And what we want to try and do is extend that to 2 and 3 dimensions, quantification of uncertainties. And this is the future. We got to figure out how to get there. And not just image, not just see below the surface, but retrieve moduli. Constrained moduli, shear moduli, Yes.
May I say, good, you know this, but you might not say it. I mean, right now in the liquefaction game, the 3D imaging is a hot topic because of, you might say, okay, this shouldn't have liquefied, this should have liquefied and so forth, but it's really the 3D characteristics of the underground in that area that are maybe starting to dominate what goes on, and we haven't paid attention to that before.
Yeah.
Fair?
Yeah, fair, definitely. We need to do a better job of that. So just a quick project highlight, which I'm going to cut through really quickly to keep us on schedule and get us to talking about the bridge that we're here to discuss. But in a couple years ago, we took our shaker truck, T-Rex, down to Christchurch, New Zealand, in the aftermath of the 2010 Christchurch, 2010 and 2011 earthquake sequence in Christchurch. 80% of the buildings in their central business district had to be demolished after a series of earthquakes. The largest was a 7.1, if I remember, 7.3, can't remember exactly. But the one that was most damaging was a magnitude 6.2 earthquake that happened right under the city. And literally, this is a very modern city with very high seismic design codes. And yet they were crippled by these earthquakes that they didn't really even expect to happen that close to their city. So we went down there to investigate the cause of the really long period ground motions. I'm not going to cover too much detail. You guys probably aren't as excited about geotechnical engineering, but we were trying to determine the subsurface stiffness down to bedrock. They didn't know where bedrock was. They had one borehole in the city that went down to 450 meters. And they were still in sand, silts, and clays, 450 meters. It's not feet, 450 meters. So we went down there to see if we could develop some really neat, non-intrusive stiffness measurements clear down to bedrock so that we could then propagate earthquake waves numerically from the bedrock up to the surface to see if we could help predict some of the destruction that happened. And we took T-Rex down there. It says February 2013. The time goes by fast. So yeah, we can move these things around. If you want to do a project in Italy, we'll go to Italy. Just get the funding. We'll be there. But no, seriously, we can move around. It wasn't even as expensive as you might think. Let's say $70,000 to ship it there.
85.
85?
No, 60.
New Zealand?
60.
Monk says 60, I said 70.
Oh, wait.
You get the picture. Okay. It's not that bad. Okay, we tested at 13 sites around the city, doing deep surface wave testing. We were trying to profile about 1,000 meters deep, not just with active testing with T-Rex, but also using ambient vibration arrays where we deploy those broadband seismometers and circles. So we would set out a linear array of geophones, and then we would shake with T-Rex in different locations. And then we would also deploy circular arrays and record ambient vibration. So we piece that information together. And based on dispersion processing and inversions of that data, which is more than we want to get into right now, we were able to identify the depth of bedrock as about 1 kilometer below the surface, with uncertainty estimates on the stiffness of that rock, as well as uncertainty estimates on all these different soil layers that alternate gravels and sands. Before our work, the maximum prior depth of the shear wave velocity profile in Christchurch was about 30 to 40 meters. So we significantly extended that through the work that we did in Christchurch. Science plan number 2, Professor Silver is going to take over.
No problem.
Thank you, sir. So Brady was saying Brady and his students that did all that deep profiling. They did a great job. Science plan number 2 was looking at non-linearity and liquefaction. And this just shows you an example. This is T-Rex, but it was T-Rex and Thumper, by the way, both of them, for a small and a high, small well control shaking and high well control shaking. We built a footing, which we changed a little differently now, but we built a footing. We had to drill through this. This is cement and loop. Nobody knew anything about this cement and loop. They do now. would just be motion sensors in this material because no pore pressure is generated. It's in the desert. And in this liquefaction, you'd also have pore pressure transducers down here, but generated shear waves going down. And basically what you saw is here is a shear modulus, and this is shearing strain, nonlinear, and you see a linear region and then a nonlinear region. And then even though one did get his PhD degree for this, he was way off with his laboratory tests. So you can see, it turned out that this material, these data were really, the Bechtel designers were overjoyed because they use these for settlement analyses. And it didn't go nonlinear, so you could use it even in the elastic range, and it got past.
Can I say something for people asking me questions? The in situ is cemented. That's why I didn't predict it. Okay.
That's right. When you ran it in the lab, you didn't have cementation, right?
That's correct.
You want to join them and have 3 young people against old guys?
I'm sure you get it right in the lab.
Okay.
Stress the importance of in situ testing. In situ testing.
I'm not retiring, it doesn't matter. Okay. So we have a lot of fun doing this, but it's really nice when it does have a good impact too, and you learn a lot. So this is going to be with the liquefaction testing in Christchurch, and no matter what it costs the Earthquake Commission, I mean, they really supported us well. So
There we go.
given the different numbers, no matter the different numbers, the Earthquake Commission did a great job. This is just a little animation, and in fact, really, I'm not sure if this is going to show just, it doesn't matter, nonlinear or also, so that's a pore pressure transducer, in fact. So it's both here, but that is liquefaction and nonlinear measurement. So we would be, that's on the back, that's the RAM on the back of T-Rex there. Install the instrumentation, then we would shake the ground and watch these nonlinear waves propagate. The bad news is, and so you see velocity V, we'll change that into displacement. So we got the frequency, and that was the pore pressure. This one is to do deeper nonlinear tests, even though, okay, there we go. And this was, we did this on a project that our dean had. So Sharon Wood was the chair of our project then, but she had a project with NSF. And we used a drill shaft, quarter scale for bridge bend. So I think it was about that big diameter. And we did put sensors in there, and you could generate a very good generator of shear waves away from that and determine the nonlinearity in the materials here. You want to talk more about the Christchurch? No problem. Doesn't matter to me. Christchurch, there was a, like Brady said, the central business district was basically destroyed. 80% had to be demolished. With homes, it was huge. And the difference there is that the property, the ground was also insured as well as the building. So their insurance said the ground would be brought back to before earthquake conditions. So they have 51,000 properties affected. You can see that's the water. That's just right after the earthquake, and that's all the sand ejected in the water. But I think it's even bigger than this. Let's just say 20,000. Now homes are more flood prone because the surface went down about a meter, in general. And it is more than that. Residential properties that have to be demolished, more than the 10,000. But you're looking at things like this. It was quite devastating. And we helped with T-Rex. Now this is a we helped with T-Rex to look at ground improvements, and they looked at compaction, but just very localized, so rapid impact compaction. They looked at building rammed aggregate piers, so they would be pushing or pounding the aggregate into the ground, building up horizontal stresses, trying to densify. And they also looked at low mobility grout. And the key point here was they were trying to build, so to get the ground back what it was, a 3 meter to 4 meter thick crust on the surface that then the structures there could sort of be on a raft, so to speak, and would perform better during future earthquakes. That was the basic idea. you know, this is just idealized, so that isn't what a ram dagger pier looks like, but here we are with our piers. We would, with T-Rex, install sensors in a zone down here, so those are motion sensors of G-phones. Those are pore pressure transducers, and then we would shake. By the way, we also did crosshole, direct push crosshole test off to the side to characterize the ground after the improvement versus characterizing the natural soil and other test panels that had nothing done there.
We may not have the sound here.
Okay, so he's saying what the problem is. Yukon was very supportive of us and very pleased with everything in the end. That's the Broadband Valley. He's telling you about the shaking, and that's Professor Stokey telling how we act like an earthquake, so to speak. Yeah, that's my earthquake. And we're at site, doesn't matter. I think we're at site 3, but so we've got this instrumentation all on the ground. It takes quite a while. Then we'll put T-Rex on top. It'll shake, watch right here. It'll shake. Oh, it's a go by. Well, no, that was at the surface. That didn't count, but that's okay. We needed it deeper than that. But they were very pleased.
Professor Stokey, which one of the ground improvement techniques showed better performance?
The ram dagger piers did the better, and with Brady, you can help me here if I say something wrong. The low mobility grouts were the only ones in the code that could be used for this, and when we did our test, we knew they were no good. They were the worst ones. Now, let me be very careful. The way they were installed was not good, and they made it looser than before the earthquake because of lifting the surface, resetting it.
Okay, so now moving on to the third aspect of our science plan. This is developing rapid in situ methods for non-destructive structural evaluation and soil foundation structure interaction. So that's kind of what we're here to see some examples of today. First, I wanted to give you just a few, kind of a broad range of how the shakers can be used in structural testing. So one approach is you can just shake the ground around the structure. There are trucks, right? So you can drive around and excite the structure through sending the waves through the ground. Another way is to shake the structure directly. If it's a bridge or a parking structure, something you can drive on, we can move the trucks and get them directly on the structure to shake. I'll also note that all of the shakers on these trucks are designed so that they could be removed from the truck, and you could attach it or some way for you to anchor it to the structure. You could do so. You could attach the shakers to the structures, and we just have the truck off to the side as the hydraulic power supply for the shakers. So we'll actually see an example of one of our shakers being removed and attached directly to a structure. Thanks. And then the last way you can actually use the trucks to do quasi-static pullover tests out in the field. You can actually set up, we'll see a video of this too. We have two trucks, one on each side. You have a winch attached to a cable. You can put a load cell line on that cable and apply cyclic loading back and forth out in the field. So you don't necessarily have to be in the lab for that. So lots of NHERI resources. There's some great structural testing resources out there. Some examples are the testing facility at Lehigh and at UC San Diego, their shake table. And this is great to understand large-scale structures in their nonlinear range. You can push these things or shake these things to far into their nonlinear range. It's really good at characterizing structural behavior. But we should also note that in the field, things maybe aren't as nice as they are in the lab. In the lab, we often idealize foundations, and we have pristine conditions and construction and materials. In reality, you have complex soils. Even for those sites where you have soil boxes where you test, oftentimes it's uniform soils. But in the real world, we may not have uniform soils. You have aging effects, corrosion, scour in your foundations, degradation. These are things that maybe you could try to simulate in the lab. Sometimes it's very difficult, but this is what's out in the field. So I think it's really important to have NHERI capabilities that can actually go out into the field and measure structural behavior that account for these non-idealized conditions that are actually out there. Now this is an example project. We're going to start a little video here. This is a project done by Sharon Wood, one of our senior personnel. Back in the early days of NHERI, this is kind of a demonstration project. So it actually built approximately quarter-scale bridge vents out in the field using conventional construction methods. Here's the drill shaft piles, fully instrumented with strain gauges and geophones that we're constructing. So I think this was in a clayey type soil. So even if you can't find a structure that's out there in service that you want to test, you can build your own specimen. And it's large scale out in the field. Here's our example of T-Rex actually coming and shaking the ground around the structure. We can shake with multiple directions. I think we're first going to see a horizontal shaking, a whole range of frequencies. Oh, sorry, vertical shaking. You can see, and then we'll see some horizontal shaking here in a second. Much lower frequency. And T-Rex can move around and show you multiple locations, collecting data, dynamic response data from our bridge vents. This is the example. This is actually a thumber shaker. This is a shaker mounted back thumber that was removed from the truck and attached to an anchor plate on the bridge vent. And this is our smallest shaker, very small force. And you can see even that small force shaker, when you're shaking at the fundamental frequency, you can see some pretty large nonlinear behavior. Here we have nonlinear gapping in the soil. I don't think you can see cracking. I think there was some cracking observed afterwards in the drill shafts. And now we're moving on to our pullover test. So here we actually have T-Rex. I think it was T-Rex. It's one of the trucks. The cable is attached. Here we see his own cables. There's a load cell there, so we're measuring force. We're actually pulling. So here we use our own instrumentation, LVDTs, inclinometers, other sensors to measure displacements, just like you would out in the lab or in the lab, but now you're actually measuring it in the field with real foundation factory conditions. Draw graphs. I'm sure all your grad students love doing that. You can see, look at that nonlinearity of the soil. There's actually hinging in that drill shaft just for the soil line.
And that's a drill shaft that we shook, a separate one, but the same size. When you saw the deeper loading.
And here we're doing the same thing to our taller bridge vent specimen, pulling very large deprivations and getting good measurements. You actually see, oh yeah, concrete's falling. Who doesn't like that as a structural engineer?
We like the gap.
And the soil people like to look at something going on down here. Yeah. I like to see a nice plastic hinge where there were your bars buckling and fracturing up at the top hinge of the column, and like I said before, they actually after the test excavated around the foundation, saw that hinging below the soil line drill shaft. And what we were also able to do here is pull all the way to collapse. So you probably wouldn't want to do it in a laboratory with an actuator, because you might damage your actuators, but we can actually pull this thing and haul it down the street.
What's the volume capacity?
What was the what?
What's the maximum push that you can apply from the views?
Drop to 70,000 pounds, T-Rex or 60,000 pounds, accounting the coefficient of friction 0.5. When you cut two side by side together, it will be 60,000 pounds.
So that's for shaking the ground, but what about for the cables?
Yeah, it's not a cable, it's a weight. When the truck starts.
Oh, for friction.
Hysteresis loops. We had T-Rex on one side, liquidator on the other. They're just pulling the vent back and forth. Yeah, it worked very well. And load cells, of course.
Is there any way to test offshore structures?
If you can get the truck there, you can shake it.
Depends on how much money you have. Absolutely, we can figure out what to do. No.
In theory, yes, you can drive a Roro boat. Drive a Roro boat. If it's big enough structure, you can shake. Talk about how to shake.
You can take the shaker with a helicopter and attach it to the offshore structure and shake the shaker so you don't need to run away, because you can detach the shaker from the.
Well, so you can see the truck is the hydraulic power supply, so you still need the truck or something to provide that hydraulic.
Yeah, if you could have another pump.
If they have a pump on site with the hoses.
They may very well have those setting pumps right on.
So that's certainly something that logistically, as long as you can figure out how to make it happen, there's nothing that says these shakers can't be used on the structure. So this is just an idea to give you typical structures. So the trucks originally were meant for geotechnical or designed for geotechnical testing, so they had a lot more horsepower for these high frequency ranges that are usually our structure charge to the soil. But even when you get down to these lower frequencies, where you have like typical bridges, like you're going to see tomorrow, overpass bridge, low-rise buildings, residential buildings, that's a huge portion of the building stock, and large-scale specimens, we can shake in this frequency range. And like we saw with Comfort with the example of that bridge, you don't need much force output if you're shaking at fundamental frequency to really generate such a large excitation. I think you might have a video of doing that on the bridge a couple weeks ago. So yeah, definitely some of your stiffer or lower range structures are best suited for your shakers. Just to give you some more examples of tests that you can do with the shakers on structures. So here's an example of a decommissioned structure. This is a bridge that was decommissioned. So that's ideally what we really want to see. We can just do whatever we want to shake it.
Wait, you got a truck on top.
You have a truck on top, but it isn't short. So
There's only one in the world. Get another one.
So we can almost do whatever we want with So decommissioned structures are great for that reason, because here they actually went into the structure in a different, the peers that were testing, they actually went in and excavated soil to simulate scour, and you can test the structure levels of scour. They went in with jackhammers and simulated different levels of earthquake damage. So this is another great option if you don't want to build your own specimen by a decommissioned structure. You can also use the in-service structures. This is an example of Kurt Germelsman, who's not here, but is supposed to be here. Did some testing using a small shaker, similar to Thunder. This was at the University of Arkansas, right, Brady?
That was your shaker, right, Brady?
Yeah.
Yeah, he was looking at dynamic testing bridges and evaluation and load rating, looking at condition assessment and things like how the mesh density of your sensors on a bridge. So we can test in-service bridges, again, just like what we're going to see example of today, and we'll put you out into the field and see tomorrow. Like Brady already mentioned, as far as instrumentation goes, we have lots of geophones. We have a fair number of seismometers and accelerometers. If you want more than that, Pascal, or can provide sensors, similar sensors for free for NSF funding minus travel and shipping costs. We also encourage you to use your own sensors if you have them. If you're already working in labs, you maybe develop your own sensors for structural health monitoring. This can provide excitation so you can validate some of those structural health monitoring systems that you're developing, or if you have instrumentation from your own lab, like LVDTs, inclinometers. And so if you can, we can typically feed those into our data acquisition system as well. Or some of you may have your own data acquisition that you can also bring to the field. We're very flexible. We'll work with you to make sure that you have everything instrumented as well. Let's see. You want me to talk about proposals? Or?
Yeah, go ahead.
So I think several of y'all here, faculty or future faculty who might be interested in using these trucks. So we are an NSF funded site, so it comes at a much lower cost if you want to use this on NSF funded projects. For my proposals for NSF, most commonly engineering for natural hazards is a new program. Much of the research that we do typically falls under this program. There are submission windows. They've changed their submission windows a little bit. Now there's one in mid-January and in September. Those are the 2 times you can submit proposals. But I want to really stress that if you submit any NSF program, any proposal to any NSF program, you can still use the NHERI shaker trucks for the reduced NSF cost. It doesn't have to be to the engineering natural hazards program. And to talk about our reduced costs, we have a budget worksheet that's posted on Science Safe, so it's a little too small for you to read here, so that's why I'm directing you. Please go to the Science Safe if you want to see more details. But essentially, if you are using the shaker trucks for an NSF funded project, all you need to pay for is fuel for the trucks, shipment of the trucks to the site, and travel for personnel. So there's no user fees for the equipment. And for this one example, the spreadsheet that we have posted on the Science Safe, there's an example you can play around with the spreadsheet if you want to see. I think this example is T-Rex going out 1,000 miles away from Texas, being shipped 1,000 miles away in the field for 16 days, and the cost came out to about $22,000 for this particular example. if you are wanting to develop a proposal and talk about budget, and some of the personnel probably much better to talk with to get a feel for how much it might actually cost to ship. You can already see the variation of ship costs in New Zealand. So if you are developing a proposal, while the spreadsheet is there for you, it's probably a good idea to also talk with us to get a better feel for costs. But just to contrast that to if you were working on now a non-NSF funded project, exact same example, 1,000 miles away, 60 days in the field for T-Rex. Now you have to pay additional personnel, overtime fees, and equipment usage fees, and for that same project, it comes out to 6.5 times more if you're not on an NSF funded project. We're also happy to talk with you about those if you want to use the trucks for non-NSF funded project. They do tell you get a lot better bang for your buck if you're proposing NSF. So the key takeaway that you get from this is if you have an idea for a proposal and you want to talk, please feel free to talk with any of us or with Mom. If you don't want to share ideas with us, that's perfectly okay. And we're happy to see how we can help you get your proposal idea on paper and make a good proposal. We want to help you as much as we can. So this is our contact information. Please feel free to contact any of us. Webinars similar to this and this one that's being recorded right now will be posted on Design Safe. We have our budget spreadsheets there so you can find out more information about pricing. But if you can't find it on Design Safe, contact us.
So just a word real quick about Design Safe. Design Safe is the cyber infrastructure site that's funded by the National Science Foundation, the company NHERI, and that's run by one of our colleagues at the University of Texas, Dr. Ellen Rathje, and her group. So like the workshops that we've conducted in the past and any project that uses a NHERI facility, ultimately the data has to be archived on Design Safe, and it has a DOI number. It's a publishable data set. You get credit for any citations to that data set, but one requirement of using the facilities is that that data has to be archived eventually on Design Safe, and we help people do that. And then that data is eventually made open access to anybody who wants to look at it and maybe process the data in a different way. That's one of the big goals that NSF has, is to support this openness of data sharing once the PI is done and has published the information so that it's out there for others to use.
Yeah, and I'll say too, that example project you saw that Sharon Wood did with the bridge fence, that was a NIST project. So all that data was posted on NIST Hub, so it has been transferred over to Design Safe. So that is data available too if you want to use that for pre-proposal data preparation. That's out there. So there's data out there that you can start looking at as well and get ideas from tests here. And all of you should be familiar with Design Safe.
I don't think a lot of the stuff that you saw was pulling the vents back and forth and so forth. I think it's there. I don't think people have used it.
Right. That was a proof of concept demonstration study where they didn't really have grad students wanted to really analyze the data, so the data needs someone to analyze it.
Yeah.
Yeah.
Well, I mean, we just advertised it last week, as a matter of fact, at another get together, and there's interest in it. But I know the project was started with Sharon Wood running it, and they were giving us some flack about, okay, we really need large motions. I said, okay, we're going to give you large motions, and we did, and they never used it.
There's also, just so everybody's aware, there are other resources available at Design Safe. To TAC, the Texas Advanced Computing Center, they tell me it's the most powerful supercomputer in the United States, but this is Texas, so we gotta embellish a little bit. So it's the best. It's a very powerful supercomputer. I use it personally in a lot of my research to run surface wave inversions. So we'll run many millions of models, okay? And it's incredible. It really is.
And I know also that Brady's daughters use it too.
Yeah. For their algebra homework. No. But
the structural engineers and also overseas, they're currently have or just about to have almost Nano as another structural element software that's going to be able to also available there, so it's a great resource. Take advantage of it. And because you went to Design Safe to register for this, you should have access to all of that right now. So take a look at it if you have.
Any other questions before we move on to the next phase of our workshop? Any questions about general equipment, or obviously just feel free to talk to us.
About the kind of data that you collect in your data acquisition, are they standardized format or
Some of the data, yes, there are standardized formats. Now, especially in the geophysical data that we collect, there's standard data formats like they're called SegY, Seg2, Miniseed, and so the data acquisition systems, some of them will spit out data in that format. In terms of other areas, though, there's not set data formats for much of the work we do. So when people upload their data, now Design Safe is trying to make it very flexible. They want the PI to upload the data in the most usable format that they would want and that they know other people in their community would want to use. So they're allowing more flexibility in the data upload, which is actually really nice, because it used to be that people, I think there was this mentality that let's try and not give too much information with our data because we want to make it hard for others to use it and maybe find something that we didn't find or beat us to the punch. But now I think we're encouraging people to be much more open and say, and give people credit for, it's like journal citations. Now you're publishing a data set, and the more people that cite that database, the better it is for you. We want people to be given credit for publishing good data sets.
Can I add on top of that? So for this project, all the data was in the same MATLAB file because it's very small. And before I hand it to the network, I give here a notebook from Jupyter Notebook, basically. So you can see, just import some library from the Jupyter Notebook, and this is open source, and just you can download for free, can use for free anyway. It's also on Design Safe. So when I give it to the net, you will see this. Oh, wait, sorry. The first column here define the folder, the name of the folder. This is where I put my data. So once I give the net, all the net had to change is just change the folder name. Everything is the same. You can run the whole thing. You'll get the same plot that I get. How it looks like, basically.
Post the raw data on Design Safe?
Yes, OPI on
Post
Design
the raw data in various forms of the process data. Eventually the PI will post that. And they're encouraging people to post their scripts, their data processing scripts. So obviously you put a lot of work into developing your processing codes and scripts, and you can, like, this happens to be an example of a Jupyter Notebook where others can come in and they can evaluate your scripts and look at what you did. And it's another form of kind of peer review, being able to look at kind of into the guts of how you process data, and they're encouraging that. But you have control. You have to publish the raw data, but you have control as a user of how much you want to share your processing scripts and stuff like that. Okay, now we are almost 10 minutes ahead of schedule. I mean, of our revised schedule. So let's take a 10-minute break. Let's be back in here, please, at 2:45, and we'll turn the time over to Professor Woods for a presentation. Yeah. You're still traveling around, Bob?
And this trip is pretty much convinced me I don't want to travel.
resistance not high. Yeah, it's when trips go bad, it really makes you question what you're doing.
Well, I
I work so much.
You have opportunity of your degree to work on
He already left. So I've met him a couple of times, but I haven't been able to interact with him. I know
he's got a lot to do.
I still read some of his stuff. In meetings, and I can't even understand this.
Yeah.
But yeah, you gotta find those people that you can interact with, merge. Discipline.
I mean,
when you find that
Are you trying to get to my email? Yeah, it seems to be. Is it possible I just get the? Is it possible I just get the slide from you?
Yeah, maybe I can put it on the front.
That'd be
We got a bunch
easier.
of video.
Oh, okay.
Soki had a foot down. I didn't give one for him.
Yeah, there's a whole presentation, whatever. That's got the videos, and if you just copy that whole thing, you should
The whole folder.
By the University of Texas group. I now understand why Ken invited me to show what I've done in the past, the old stuff. And you'll see the contrast. Oh, enormous.
Did you not want to know that we could identify you? I can hardly read. Who is this speaking? Woods. Wow.
Oh, this is just a NEAC member. NEAC is a committee, the oversight committee for the NHERI. Anyway, and I'm a member of that, so I am here officially, and in an unofficial role, he has called me in to eat my humble pie on this sort of thing. But I hope that you will all agree with me sort of in the end that it's all a matter of scale. And I have only one example where I can beat any scale that Stokey can throw at. So we'll see that a little bit later. Now, I start out just in passing with a static test. One of our faculty at Michigan has for many years loaded bridges statically to determine whether the estimates of settlement were or deflection were as computed. And he used M60 tanks. This is Professor Andy Novak, who is now at Auburn University. All right, now we'll talk about exciting civil engineering. And I think the whole idea is that we want to do something to a structure, or for most of us here, the ground, that results in something that's exciting. Simply mean it is moving. It's not static like the tanks. So we'll start out with AREX. Stokey now has T-Rex. This is Stokey AREX. We have here a model footing.
A very pretty model footing, by the way.
Oh, yes, of course, it's the wrong color. It's not either blue and it's not burnt orange or whatever that ugly color is. In any case, there are instruments on here to measure motion. But one of the ways of exciting is plucking. And you pluck the guitar and so forth. Well, this is an example of plucking. You can't see it, but there is fish line going up from the corner of this footing, upward, over the pulleys, downward, and here is a weight hanging on that fish line. This is exciting. And how do you pluck it? Well, you hold this board up next to the fish line and you cut it with a hatchet. This is AREX, not T-Rex. But it was effective. You pluck the footing, you find out what its basic mode of motion might be. And this is the facility in which Stokey was doing that work. It turns out that two of these facilities have grown after this one. One of them at Rutgers University and one at UMass. Currently, the Michigan testing facility is in the floor, not above the floor, but at that time we couldn't win. In any case, here is our erstwhile investigator. This isn't his test, though. This is my thesis, and he was my laborer. So exciting. Plucking is one way. Steady state vibration. At the time that he and I were growing up at Michigan, this was all we had. And it had about a 25-pound force capacity. And it allowed us to do linear testing, strictly linear. This happens to be a place where we're testing the impact of the effectiveness, I guess you should say, of a trench as a barrier to vibrations. Okay, so plucking and steady state, they're essentially all we have when we get into exciting business. Here is another exciter like the electromagnetic. This is just a electric motor, linear motor, what one could say. And there is an armature in here that is forced to go up and down in this direction. But of course, you can mount this device in a lot of different ways. And in this particular case, it is exciting the vertical motion of a group of piles, model piles, in that experimental bin. And well, you notice they've got a stack of plates on them. Why do you do that? Well, you have to get the system into the frequency range of your exciter. And that's the only way you can do it. You've got to add mass to the top of the exciter. Well, steady state. We can do steady state in some various ways. Of course, hydraulic is one possibility. Electromagnetic is another. And here is a mechanical approach. This is a Lausanne oscillator named for a mechanical engineer at University of Minnesota. And it simply has a drive shaft, a DC motor, and the internals look like this. Here is the drive shaft, and these copper color elements are eccentric masses mounted to these two shafts. And the shafts are counter-rotating, and so you can develop a force in one direction with rotating masses. And this device in a certain frequency range could develop forces, maybe 6,000 pounds at maximum, but nothing like 50,000 pounds that we get with T-Rex. Now, plucking doesn't always mean pulling on something and letting it go, or pulling on it and chopping a wire. It can mean just bumping a structure. Here is the ground floor and the lowest elevation of a structure which carries on then up through the floor up to a certain height. This is a glass draw tower for Corning Glassworks, and it's one on which they manufacture optical fiber, glass fiber. The key is that they mount an electric furnace up at the top, they heat up the furnace, and they mount in the bottom of the furnace a gob of glass. The glass melts, and it forms a little string, a thread coming out the bottom. They grab that thread and they put it through a die at about this elevation, and the die is intended to make the glass uniform diameter. You can't have the glass doing like this, or it reflects internally the light that you'd like to project to whatever distance you're working at. So in this case, it was an issue of designing these towers such that they were mismatched to any frequency of the draw system. And to do that, we would test the towers after they were built by standing on this second floor and a lineman's block. And it set it into motion, and these were very lightly damped steel structures.
Is that the way you used to block when you were a lineman?
I don't know. But I didn't want to fall against the top of
Is that a Notre Dame block that you're showing there?
Yeah.
Okay. Just for the record.
That's a Frank Leahy block. I don't know how many know Frank Leahy. Anyway, these draw towers started out, we started in 1976, and they were 28 feet tall. And by the time we finished late 80s, they were 72 feet tall. And the idea was, how fast can you draw the glass out of the gob? Because it has to cool enough to be able to go through the die. And all this. Anyway, plucking. And it worked quite well. Another plucking situation. I'm sorry, the light's a little bit bad, but this is a helicopter. This is the medevac, University of Michigan Hospital. It's coming down on a roof. Below that roof is the first stage of emergency treatment. And the roof was vibrating too much. How do you check out the roof? Well, there's a parapet along here, and my colleague and I, Larry Yadley, would jump off the parapet onto the roof. Plucked it, and we got the natural frequency. Now, here is a single pile, and it has a certain weight of mass on top so that we can, so it will respond at frequencies at which we can excite it. But we can pluck this too. Now, you can't pluck it and get nonlinear data, but we can pluck it only for the elastic range. So here's, oh boy, yeah, our lights aren't doing too well. Here is a stack of plates on top of a pile. Here is another pile in which we have a framework built up with a cable running through to grab that pile. And turnbuckle, we would pull on the pile, and instrumentation on this side, not shown well. And the pulling rod is over here, and there's a segment on the fixed side of the cable that is nylon rope and force transducer in it. And we have to thank Professor Stokey for the suggestion. It's out in here, and what do we do with it? Whoops, went too far. Anyway, there is we place a board on the ground. You see the cable is close to the ground. Axe. We went up a scale from a hatchet to an axe. And we would pluck the pile and it would vibrate. And the whole idea was, like this one, was to excite it in a linear elastic mode. But here we have mounted the Lausanne oscillator on top of the pile, and the motion of the oscillator will cause the pile to deflect in this direction. I don't have a movie for you.
Where is that?
Monroe Power Plant, Monroe, Michigan. So this is the Lausanne oscillator, steady state, and again, we're trying to match measurements with predictions, and our prediction technique was based upon the Baronoff elastic side layer theory. And I think probably in this room, Professor Gugunski is most familiar with those programs. In any case, we were trying to compare with prediction. And here was a model study piled groups. And we start out in that sand bed again, a pit, coordinate system. Piles were installed, embedded with our tips, and then filled in, vibrating the sand around the piles. And so the idea was to test the response of piled groups, groups of 2 and groups of 4. And one way is with the linear motor. Exciting, here is the stack of plates on top of the model piles. We still had to get them in the right frequency range. And so steady state excitation. Now, steady state excitation out in the field. We saw a multitude of different levels of force available in the Texas system. This is running SASW tests along the shoulder of Interstate 70 in southeast Ohio. And here is the vibrator, probably much like your thumper, 6,000 pound force capacity, something like that. But looking for old mines, coal mines in southeast. Now, as I said, I have one big steady state that goes beyond anything Stokey has been able to show you.
Is this the mother of all bombs? Is this what we're looking at here?
Yeah, sort of.
Okay.
Yeah. Okay, we want to shake that dam. The dam's 2 miles wide. We want to shake the dam. Dam. And it's 460 feet high. The issue was this is in the foothills of the Himalayan mountains and a highly seismic zone. And the whole issue was what might its natural frequency be and what is the magnification toe to crest. This is the same dam looking from the other bank. And on the other bank, in the rock abutment, there are 4 tunnels. 2 of the tunnels are for generating electric power going into power plant. 2 of the tunnels are for irrigation. Trouble is, there was a major catastrophe. And if you were around in the mid-70s and reading Engineering News Record, you read about it. But I don't see many of you here who were around to do that at the time. In any case, Tunnel 2 at the upstream end collapsed. And there were a lot of reasons for that happening. And the poor guy who allowed that to happen committed suicide. But in any case, this is what happened to Tunnel 2. And it was an issue of a temporary gate being jammed partway open, not fully open, not fully closed. And it creates such turbulence that it destroyed Tunnel 2. But that created an opportunity for measuring the natural frequency, first mode, upstream, downstream, horizontal motion of this dam. There are at least 9 zones of soil here, soil and rock. And a group of our faculty at Michigan, Streeter, Wiley, Richard, and a couple of their grad students modeled this dam, modeled this cross section with the method of characteristics, and did a pretty good job of it. In any case, they estimated that the natural frequency was about 1 hertz. Well, how do we excite the dam to find out if that's true? And excite it at different frequencies? Well, Professor Streeter had the answer to that. Because when water is flowing in these tunnels, depending upon the elevation and the pressure at the upstream end, they will act like organ pipes. First mode looks like that. And even with the water flowing, there is still the organ pipe motion. And how do we know? Well, we installed accelerometers. And I neglected to mention when I showed you the 4 tunnels, there are locations of 8 transducers. We installed these to measure frequency. And so the transducers, accelerometers were in these 2 tunnels, which allowed water to flow for irrigation purposes. The total water coming out of these 2 tunnels in these 2 pictures is about the same as the water in the Detroit River passing Detroit at one time. It's 125 miles an hour in these tunnels. And the hydraulic head here, where the fast water meets the stilling basin water, 100 feet. Well, so we installed pedestals. These pedestals were there for light posts later on. Anyway, pedestals both at the crest and at the toe of the dam to measure the both vertical and upstream, downstream motion of the dam. We located them at the 3rd point and the 2/3 points, 2 places along the length of the dam. And so at the crest and at the toe, looking for the magnification. And the question was, can we control the elevation? The only time we could do that was when they were repairing the Tunnel 2, which was destroyed in the accident. So we started out with a reservoir elevation, it's at about 15, 20, something like that. That's in feet. And then as we let the water flow out of tunnels 3 and 4, then the elevation dropped. But we had measurements at the crest. Here's 1/3 point, 2/3 point, and toe 1/3 point, 2/3 point. And as the elevation came down, the magnifications diminished, but the frequency changed. And we were able to see a spike essentially in this region. And all of the data isn't there because it's concentrated on another plot that I didn't give you here. In any case, we measured about 0.96. And so we had a active excitation in steady state of the entire 140 million cubic yard dam. Yeah, I was there. I was making the measurements. Now, sometimes we have unintended steady state. And how might that be? Well, look at these old-fashioned T-Rexes or liquidators or whatever the heck they are. These are from probably late 70s. And there are 5 of them lined up there in what they call a conga line. And the geophysicists then moved this conga line en masse from this location, half a mile down, half a mile down. They set it in excitation, measure ground motion up and down this road for long distances, and evaluate the underground, get a profile looking mainly for salt domes, but whatever, produces oil. But in the next step, the geophysicists were not very cautious.
This is northern Michigan.
Yeah. They liquefied the end of the lake. And you can see 3 of the trucks are in the drink. One of them is sitting up here, and the other one is out of the picture. Fortunately, they're pretty low. Literally. fortunately, they're pretty robust tools, and they were able to dry them out and clean them up, and they all operated. So that wasn't too serious, although I suppose that they lost a lot of time in making that cleanup.